chapter 1. Chapter 1 is about basic definition on commutation monoid and heaps of pieces. So I just remind you what I have done the first lecture. So a brief summary of the previous lecture. I define the commutation monoid as the following. You have a binary relation capital C, which is called the commutation relation. And I define the congruence generated by this relation. This relation is symmetric and anti-reflexive, which means A commutes with B, but A does not commute with A. It may be strange, but that's the rule. And we define the congruence generated with equivalence class. Here is an example of equivalence class for the word A, B, C, A, D. This is the 5 words which are equivalent by doing some commutation of consecutive letters according to the commutation rule defined by the binary relation C. And then the commutation monoid is defined in the following very obvious way, that the product of two classes is a class of the product of the word, and this does not depend on the choice U and the choice V as a representant of the commutation class. So this monoid was introduced by Cartier-Foata a long time ago in 1969, and it was reinterpreted by your servitor in terms of heaps of pieces. So this is the general intuition behind heaps of pieces. This is a heaps of diamonds on a chessboard. They are supposed to fall down one by one on the chessboard. Each diamond is a projection, which is a union of two consecutive cells, black and white. And when you see this picture, you forget in which order the diamonds fall down, but what you see is the intuitive idea of a heap. So here is a basic definition of a heap. You have a set P of basic pieces. You have a binary relation C bolt, which is called the dependency relation. It's again a C because in French, it's relation de concurrence, which is not the same meaning in English concurrence, but it can be a competition relation. C for competition. And a heap is a finite set of pairs. Alpha is a basic piece, and I is an integer, which is called the level of the piece, satisfying these two conditions, these two axioms, that if two elements of the heap are at the same level, then they cannot be in concurrence, in dependence. And if you have an element of the heap at level I, then there exists somebody below at level I minus 1, such that the projections are independent for the relation C bolt. So this is the main definition for all this class. And then I define the heap monoid, the product of two heaps, as to be. You have a heap E, a heap F, and the product is in this following picture, is symbolized by this picture. And this is an example. This is a heap E in red, another heap F in blue. If you take the union of the two, then they are going to overlap each other. But the product in this case is the following. You put the blue heaps very high enough to all the pieces of the blue are above the pieces, the level of the pieces of the red. And then you make the blue fall down, and you get the product of two heaps. So we have seen last time an equivalence between commutation monoid and heap monoid. So for any word in basic pieces, alpha 1, alpha 2, alpha n, then for any word, I define a heap as a product of the pieces alpha 1, alpha 2, alpha n. You put as a product as a heap, you put the first piece alpha 1, then alpha 2, then alpha 3. You put them one over another. And I take the commutation relation to be the complementary of the dependency relation. Example, for example, heaps of diamonds. You take the basic piece to be the pair I plus 1. I call this generator sigma I. So the dependency relation, two diamonds are in dependence if and only if the intersection is non-empty. And the complementary of this relation is a commutation relation. Two such diamonds commute if and only if. So as a subset I plus 1, they are disjoint, which means that the distance between I and J is bigger or equal to 2. There should be some animation, and animation is destroyed. An example of a heap associated to a word with commutation. Like this, you have a word sigma 2, sigma 3, sigma 5, sigma 4 in the dimers, and you have seen the dimers fall one by one, and from this word, you get a heaps of dimers. So from a word in basic pieces, I get a heap, and there is two fundamental lemma that if two words U and V commute, if they are equivalent for the commutation relation, then the two heaps are the same. And conversely, if two different words give you the same heap, then they are equivalent for the commutation relation. And from these two lemma, lemma 1 and lemma 2, then you can define a map phi bar, which is defined by this commutative diagram, which send any classes of the commutation monoid onto a heap of pieces. And I claim that this map phi bar is an isomorphism of monoid. So the two monoid I have defined, the heap monoid, where you have the product of two heaps, is equivalent, is isomorphic to the commutation monoid. The alphabet on this monoid is the basic piece. Here is the basic piece. And the relation between the two binary relation is this relation C is a complementary of the dependency relation. So we have finished by claiming this last time. Now I'm going to give a proof of these two lemma and of this proposition, that we have the same picture in terms of words or in terms of heaps. So proof of lemma 1 and 2 and of the proposition. So lemma 1. If you have two words equivalent for the commutation relation, then they give the same heap. This is obvious. Let's go back to the example. Here is a word sigma 2, sigma 3, sigma 5, sigma in terms of dimers. And here is a heap. If I have, this is in red, sigma 2, sigma 3, sigma 5, sigma 1. Then I have sigma 4, sigma 1. I am going to permute to make a commutation between sigma 4 and sigma 1. So I first put sigma 4 and then sigma 1. And then I put sigma 3. And this is the same as first putting sigma 1, then you sigma 4 from down, and then you put sigma 3. So this is obvious in general. If two words are equivalent by the commutation relation, then they give the same heaps in terms of heaps of pieces. Now lemma 2, conversely, if two words give the same heap, then they are equivalent for the commutation relation. So the proof of this lemma relies on what is called the Cartier-Foata normal form. So we go back to the commutation monoid. This is a kind of canonical form for any element, any class of this monoid. So it is one of the first theorems in the lecture note of Cartier-Foata in 69, that you take any element. This is an equivalence class of the word W. This notation means equivalence class for the commutation of the word W. This is an element of the commutation monoid. This is another notation for the commutation monoid with alphabet A and commutation relation C. This was the original notation of Cartier-Foata. So any element of the commutation monoid has a unique decomposition in terms of block W1, W2, etc., WR. This is a product of equivalence class, satisfying the following condition. So first condition, in each WI is a word where all the letters commute 2 by 2. I put in between bracket commute. Commute means that for the relation commutation C. So you see, if you take any word, any letters Y and Z inside the word WI, each pair of letters commute. And commute means that they are distinct. because the letter does not commute with itself. So all the letter, all in particular, all the letter in each wi are distinct because the relation C is anti-reflexive. So in each block, the letter commute 2 by 2. Second condition, if you take an integer j and the block number j and the block number j plus 1, every letter z which is inside this block, the block j plus 1, there exists a letter y in the block just before, the block number j, such that it does not satisfy the binary relation C, which means y and z does not commute. So in W2, see, there is always each letter does not commute with one of the letters of W1. In W3, each letter, for each letter, there exists a letter before which does not commute with this letter. And such decomposition, satisfying these two conditions, is unique. You go too fast. No, I start slowly for this class. I don't go too fast. Usually I will go very fast. I go too fast when I give lecture, but I try to go. So if I go too slow, then you tell me. But so proof. So I define F1, the set of letters Y of the word W, such that W is equivalent for the commutation with a certain word Y multiplied by a certain V1. What does it mean? It means we take a word W, you take a letter Y, such that by acting the commutation, Y can be bring at the first letter of the word. By doing the commutation, you can bring this letter Y at the first letters. Maybe there are several different letters which can be put at the first letter doing the commutation. I call F1 the set of all these letters of the word W. So first fact, the letter of F1 commute 2 by 2. Because suppose Y and Z are letters in F1, which means that Y, you can bring Y in the first position, you can bring Z in the first position, so sometimes Z has to commute with Y to be put in first position. So all the letters in F1 commute 2 by 2. And I call in bracket W1 the product of all the class of the product of all the letters in F1. So you see, the word W1 is not unique, but all the letters of the word W1 commute 2 by 2. So I take the product of all these letters. And then I can always write W equal W1 multiplied by something. And now I can define F2, the set of letters of W, such that you can bring the letter Y just after the word W1. Maybe you can bring Y further inside the word W1, but you will not be able to bring Y at the first position. So I define F2 to be all this set of letters, which can be by commutation put in a position just after the word W1. And again, W2 is, I define bracket W2, the equivalence class of the product of all the letters of F2. The letter of F2 commute 2 by 2. Again, the same argument as here. And each letters of F2 does not commute with one of the letters of W1. Instead, you can bring the letter at the first position, etc. F2, F3, F. So I have defined a sequence of blocks such that each letter, in each block, all the letters commute 2 by 2, and each block, any letters, does not commute with one of the letters of the previous block. Example, if I take this word with the dimers, commutation 2 sigma I commute if and only if the distance between I and j is bigger or equal to 2. This is a generator of the symmetry group and many other algebraic structures. So what are the letters you can bring in first position? Sigma 2, of course, and sigma 3 you cannot put in first position because the difference is only 1. Sigma 5 you can put in first position, and that's the only one, only letters. Sigma 1, it's impossible. Sigma 4, no. Sigma 1, no. Sigma 3, no. So this is the first block. Now what are the letters you can bring in first position in this word? So sigma 3, sigma 1, and not the commutation. Where are my dimers? And now that's how way is it? Here. So it's the commutation relation. Sigma I and sigma j commute if and only if the indices I and j, the difference is bigger or equal to 2. And in terms of Heaps, it's sigma is a subset, I plus 1, and the dependency relation if and only if the two segments are disjoint. Here you can. This is a summary of so Cartier-Foata normal form. Okay, so now you have this word. What are the letters you can put in first position? Sigma 3, sigma 1, because the difference 3 and 2 is 1. Sigma 4 is impossible, because it's close to sigma 3. Sigma 1, no, because it's going to hit sigma 1. Remember, sigma 1 does not commute with sigma 1. And the difference is 0. It's the worst case not to commute. And sigma 3 cannot be put in first position, because sigma 3 is going to hit this sigma 3. Commutation means if they are identical, if the two pieces are identical, you cannot commute. So the second block is this one. Now sigma 4, sigma 1. So you can, so this is the third block and the last block. So this is called the Cartier-Foata normal form. A normal form is a kind of representant for the commutation class. So unicity is obvious, because if you have the first block of letters commute 2 by 2 are exactly F1, the one I have defined, F2, etc. You can convince yourself that there is a unique factorization.
In the second step, you could have done sigma 1, sigma. You could have done a commutation of sigma.
Yes, in each block, in fact, you can commute sigma 1 and sigma 3 here. They commute, huh? In fact, the Cartier-Foata normal form, you see, within a word, within a block, all the letters commute 2 by 2. So I have defined W1, one of the representants, but you can you take the product of distinct letters. So the word is not unique. It's the class is unique. The class.
No, so what I'm saying is, can you go to the example again? So what I'm saying is, why did you keep sigma 3, sigma 1? Why did you not? You would have done a commutation of sigma 1, sigma 4.
Which sigma? You are talking of the
second step.
Second block here? Here.
Yeah. So kept the sigma 3 and done a commutation of sigma 1, sigma 4.
Yes.
So then sigma 4 cannot move to the left.
Yes, sigma 1 can be put in first position. The definition of F2 is all possible letters here which can be put in first position. So sigma 3 can be put in first position. Sigma 1, I can put it in first position because sigma 3, sigma 1 commute. But sigma 4 now cannot, because it's going to be in competition with sigma 3. The difference between 4 and 3 is only 1. Sigma 1 cannot be put in first position because it's going to be in competition with sigma 1. The rule is important, that sigma 1 does not commute with itself. It's in competition with itself. And sigma 3 also cannot be put in first position. So I have this second block. Now sigma 4, sigma 1, okay, this can be put in first position, this can be put in first position. Sigma 3, no, because it's going to be in competition with sigma 4. So that's the only letters which can be put in first position. So in each block, all the letters are distinct, and they commute 2 by 2. Any pair commute by itself. And in each block, if I take this block, any letters like sigma 4 doesn't commute with one of the letters of the previous block. So sigma 4 is in competition with sigma 3. Sigma 1 here is in competition with this sigma 1. Okay, I can go on. So unicity, you can convince yourself that it is obvious. Now what is the relationship between the Cartier-Foata normal form in the commutation monoid and the relation in terms of heaps of pieces? So I'm ready to guess immediately the relation that in each block Wi corresponds exactly to the element of the heap phi of W located at level I minus 1. So this lemma, you see, if I take this word, sigma 2, sigma 3, sigma 5, this gives you this word sigma 2, and then sigma 3, and then sigma 5, and then sigma 1, and then sigma 4, and then sigma 1, sigma 3. So this word gives this hips. Now if you take the Cartier-Foata normal form, so the first block, all the letters which you can put in first position. A letter here will be in first position. If and only if the corresponding hips, corresponding pieces of the heap is at the 0 level. Sigma 2, sigma 5, you see you have sigma 2, sigma 5 at level 0. And then by recurrence, the second block, sigma 1, sigma 3, will be these two dimers at the level 2. For level 0, 1, 2, 3. So each block corresponds exactly to the letter at level I. It's because the block at level 0 are exactly, letter at level 0 are exactly the letters you can put in first position in the word W. So this lemma is obvious.
If you know the heap for the heap that corresponds to this, can you, like the anti-heap, if you push it to the top, can you get any information of that?
Yes, if you put you mean putting all the pieces, putting gas helium inside and putting all the, and then the pieces, so you will get these two, so you will get the pieces on the top will correspond to the Cartier-Foata normal form, but from right to left. In fact, there is two Cartier-Foata. When you read the word from left to right, or when you read from right to left.
But the blocks are different.
So the block will be different. It will be this block here. We will go back to this. So we will go back with the minimal. This is a minimal piece at level 0, and we will go back with the maximal piece. So we have now proof of lemma 2, of this lemma, using the Cartier-Foata normal form from left to right. This is so here is a word in red, give you a certain heap. The word in blue give you another heap. They give the same heap. So lemma 2 tell you that the two words are equivalent for the commutation. But giving the same heap, because of the relation between heap at level with the pieces at a certain level in Cartier-Foata normal form, this means that the two words have the same Cartier-Foata normal form. I switch off my phone. So the two words have the same Cartier-Foata normal form, so they are equivalent for the commutation relation. So again, this is obvious. So we have proved lemma 1 and lemma 2. From lemma 1 and lemma 2, you can define a map, a bijection, between the commutation class and the heaps of pieces. And I claim that this is an isomorphism of monoid. I claim the map that sending, see this map, when you have an equivalence class, you take any equivalence class of the word U, you take any representant, this gives you a heap of pieces, and this heap does not depend on the choice of the representant. and I have to prove that, in fact, it's an isomorphism monoid. So remember the product of two heap, product of two class. You have to convince yourself that it is isomorphism monoid. I will not go in more formal proof, but convince yourself that taking the product in the heap is equivalent to take the product in the class. Okay. Convince yourself. One exercise. People shouldn't ask some exercise. It's difficult to give exercise straight away, but so using the Cartier-Foata normal form, prove that the commutation monoid, how do you say in English? It's you can simplify from left or right. If you have a product UV equal UV prime, then V equal V prime. Cancellation, simplifiable in French. You can cancel on the left or you can cancel on the right. So you can define the deletion when you have a heap. Take a piece above the heap, then you can delete. You can take off the... Oh, there is many proof. If you with heaps, it's more obvious. If you take heaps of pieces, the left cancellation is more obvious. And if you take anti-heap on the ceiling, then the right cancellation is obvious. But try to keep only the Cartier-Foata normal form and Cartier-Foata commutation monoid. Now the second form, which we will use many times in this class also, in terms of heaps, to find bijection, is called the lexicographic normal form. Sometimes it's called the Knut normal form because it appears in the paper of Knut, but Knut is not happy with this because he did not agree, so I will keep the term lexicographic normal form. So so you suppose you have a total order, define a total order on the basic piece. And I define, so the minimum, when you have an equivalence class, I will take the minimum letters. Minimum letters, the letter you can put at the beginning. This is the minimal letters. I will call it the minimal letters of the equivalence class. So I will define Knut or lexicographic normal form in terms of commutation monoid. You can translate this in terms of heaps of pieces. So let's define the minimum letters of a class. Any letters you can put, any letters of the first block will be a minimal letters. So the minimum letters are exactly the letters of the first block of the Cartier-Foata normal form. So minimal letter means that the piece in the associated heaps is exactly at level 0. So minimal letters correspond to pieces at level 0. Here is my favorite example with dimers. In blue, you have the minimum letters or the minimum heaps, minimum dimers corresponding to the letters, sigma 2 and sigma 5. And lemma, in the commutation class of W, the smallest word, V1, V2, Vn, for the lexicographic order, you have a total order on the basic pieces. Basic pieces P is the alphabet of the commutation monoid. So the smallest in the lexicographic order is obtained by the following process. You take V1, the smallest minimum letters of W. There is, in the first block of the Cartier-Foata normal form, there is many different letters, but you take the smallest for the total order of the basic piece. So you take V1. Then you take V2, the smallest minimum letters of what remain the word W2, etc., etc. So you take off one by one each minimum letters, and among the minimal letters, take the smallest for the total order of P. And lemma, what you get is exactly the smallest word for the lexicographic order in the commutation class. So I leave you, it's more or less obvious, I leave you as a proof of this. but we can define this in terms of heaps. So I take the example again of dimers, of the commutation of the generator of the symmetry group, and I take the total order here, sigma 0 less than sigma 1, so total order of the integer, 0, 1, 2, 5. And then I'm going to extract the Knut normal form. So take the minimum letters. Minimum letters are the 2 letters at level 0. This is the minimal letters of the word. And take the smallest. So it's sigma 2, between sigma 2 and sigma 5. Then I delete sigma 2. What I get is a heap associated to the word when I have deleted the first letters. Now I have 3 minimal letters. I take the leftmost, which is sigma 1. I delete it. Take the smallest of the dimers at level 0, sigma 1. Now the smallest is sigma 3. So each time, you see, you delete your dimers in terms of heaps. Take the leftmost dimers at level 0, and then you extract slowly. So sigma 5, sigma 4, and sigma 3. So I claim that this word in blue is equivalent, of course, to this word, and this is the smallest in the lexicographic order of this word. So this is another normal form, a canonical representant of the equivalence class of this word. So you see, we have given, we have a heaps of, in terms of heaps, there's a heaps of pieces, and I have deleted one by one these dimers, 1, 2, 3, 4, 5, 6, 7, in a certain order. So I would be able, I have defined minimal letters of a class. I would be able to define maximal letters of a class also. It's a letter you can put at the end. So this is in terms of commutation monoid, minimal and maximal letters. And in terms of heaps, this is in blue. This is sigma 1 and sigma 3. So you see, this is the 2 letters in the word which are maximal letters. But maximal letters, you see, they are, maximal letters means that in terms of heaps, it means that it's some pieces that if you take, you can evaporate the piece. You can take it and put it up without being in competition with any other pieces. But you see, when you take the Cartier normal form, the last block is sigma 3, and this is not the maximal letters of the word. The maximal letters are these 2, and it would be the first block, but in the Cartier-Foata normal form from right to left. And if I am putting some helium in each dimers and all the dimers go to the ceiling, then this blue will be at the maximum level when everybody go up to the until the ceiling of the room. And in this class, we will meet many times the heaps of dimers with only one maximal piece, or commutation class with only one maximal letters. So I will call this a pyramid. Pyramid when there is only one maximal letters. If there is only one minimal letters, so all the heaps rely on only one piece, it would be a cone or anti-pyramid. The pyramid is, the head is on the floor. So this is pyramid of hexagon, which is the interpretation of a very famous genetic function in statistical mechanics. This is related to the hard hexagonal model of Baxter, and to count something, it's to explain, there is a formula, but to explain it, it's an open problem. Another exercise, quasi-partition of integer. So everybody knows what is a partition of an integer. Here n equals 43, and a partition is just a sequence, non-increasing or weakly decreasing numbers, such that the sum of all these numbers is equal to 43. It's partition of an integer, and usually a partition is visualized by what is called a Ferrer diagram. It's a diagram like this, where each row is exactly the number of elements in each row is what is called the part of the partition. See 6, 6, 6, 5, 4, 4, 4, etc. So you have this kind of diagram, which is a visualization of the partition. So what is a quasi-partition? Quasi-partition, it's an extension of partition where lambda, it's a decomposition of the integer n into strictly positive integer, such as that lambda I plus 1 is less or equal to 1 plus lambda I. Instead of being less or equal to lambda I, it's less or equal to lambda I plus 1. So this is a visualization of a quasi-partition. I have a quasi, see 4, 4, 3, 1, 2, 3, 2, 1. So the number go decreasing, weakly decreasing, but sometimes it can increase by 1. So here it's like a partition, but between 1 and 2, it's increasing by 1. 2 and 3 increasing by 1. So at most, the sequence of integer is decreasing weakly or maybe increasing by 1. And to put an analog of Ferrer diagram, you see it's a 4, 4. So I put in diagonal this orange cell, and then you put any diagram like this. The upper border is like a Ferrer diagram. In red, you have a border of a Ferrer diagram, and you delete all this. And if you count the number of cells in color, so you have 4, 4, 3, 1, 2, 3. So you see, when you go up like this, then the number go increasing by 1, but cannot increase more than 1. So this diagram is exactly a visualization of this condition. So it's less common, less usual than partition of integer, but this one introduced by Andrews, maybe we'll look in future on, but Andrews used this quasi-partition to give an interpretation of what we call the reciprocal of Roger-Ramanujan identities. And this Andrews theorem, you can reprove it using heaps of pieces. So the exercise is the first part of the proof, and I will give you in a chapter about continued fraction and Ramanujan. In 1 month, I will give you the complete proof of Andrews theorem. But this one introduced by Andrews, and the exercise is the following. This is the first step to reprove Andrews theorem by using heaps. So using lexicographic normal form, find a bijection between heaps of dimers on the integer, non-zero integer, and quasi-partition, such that the number of k of parts will be the number of dimers of the heap. So any heaps of dimers, no condition on the heap, will be in bijection with a quasi-partition, such that each dimers will correspond to a part of the quasi-partition. And second question, once you get your bijection, find an interpretation of the number n, which is a sum of all the parts of the quasi-partition. Exercise. It was exercise 0. 2 more exercise. It's following the exercise 1 about quasi-partition, but instead of taking a general heaps of dimers, take what is called a semi-pyramid of dimers. So pyramid of dimers is a heaps of dimers on the line having only one maximal piece in blue. Semi-pyramid means you are on the positive integer, or 0, and the unique pyramid is a unique maximal piece as a projection 0, 1. So the shape is like a semi-pyramid. You cut a pyramid in two, and the top of the pyramid is touching the vertical axis. So we call this, especially in Bordeaux, in relation with directed animal and physics, we call it a semi-pyramid. The unique maximal piece as a projection, the dimer 0, 1. And amazingly, the number of such semi-pyramid is the Catalan number. So it's famous number, we will meet many times the Catalan number, which is 1 over n plus 1, the binomial coefficient 2n chosen.
And what is n in this?
And the number of dimers. Yes, exercise using exercise 1 about quasi-partition and lexicographic normal form. This is exercise 2. Find a bijection. So you have to use the first bijection with quasi-partition, and you go to Catalan numbers. Find a bijection between semi-pyramid of dimers having n dimers and dict path of length 2n. The exercise is not to try to find a proof, direct proof of the fact that the number of such thing is Catalan number. Maybe it's too difficult at this level if you don't have any notion of generating function or all the technique of enumeration. But the exercise is the following. We know that, for example, here, example, there is 5 semi-pyramids. Catalan number is 1, 2, 5, 14, 42, etc. So you check, there is 5 semi-pyramids with 3 dimers. So I suppose you know, in the exercise, you know that dict path, we'll meet many dict paths in this class, last year. So a dict path, it's a sequence of points in the quarter of the lattice, starting at the point 0, 0, and going up or down, elementary step. You go to the next neighbor at the northeast, or you go next neighbor at the southeast. So this is a dict path, you see. And it is well known, so we suppose that you know this, that the number of dict paths is exactly given by this number, the Catalan number. And then the exercise is just to find, using the bijection with quasi-partition and heaps, find the bijection between semi-pyramid of dimers and having n dimers and dict path of length 2n. There is a different way to do the bijection, but this is using quasi-partition, which use a lexicographic normal form, using Knut normal form, apply to semi-pyramid, you get a bijection with dict path. And finally, exercise 3, a little more difficult. If you take pyramid of dimers now, instead of semi-pyramids, pyramid of dimers, so there is on Z, it's there is no limit on the left and the right of the pyramid. If you take pyramid of dimers on the integer Z, so up to translation. So the number of such pyramid with n dimers up to translation is going to be exactly half of 2n chosen. And what is 2n chosen? The exercise is 2n chosen is given by the number of bilateral dict paths. This is obvious that bilateral dict path. Bilateral dict path means you start at level 0, you finish at level 0, but maybe you go above or below the x-axis. So such bilateral dict path is encoded by a word in 2 letters, x and x bar, such that the number of x is exactly the same as the number of x bar. X means you go up, x bar you go down. That's elementary northeast or southeast step. So the choice of such a word with letter blue and red is exactly the binomial coefficient 2n chosen. There is n different way to choose. It's just a subset of n element above 2n element. So bilateral dict path is exactly given by the binomial coefficient 2n chosen. So this is obvious to see. And then exercise 3, using exercise 2, the bijection between pyramid of dimers such that the projection of the maximal piece is 0, 1. So exercise 2, find a bijection between pyramids of dimers on Z such that the projection of the maximal piece is 0, 1. It's a pyramid up to translation, so I can fix the maximal piece to have the projection 0, 1. So such pyramid of dimers with the dimers being 0, 1 are in bijection with bilateral dict path starting at up northeast step. So such paths are given by half of 2n chosen. So this will give you the 2 problems. Semi-pyramid and pyramid up to translation are counted by Catalan number and half of 2n chosen. And all this can be bijection coming from the lexicographic normal form. There is also bijection, which will be chapter 3, between bijection between a path and a heap. But at this level, you can do the bijection using only commutation monoid or normal form. So now this next section is about poset, partially ordered set. So what is a poset, a partially ordered set? So you have an order relation. You have a certain set E and an order relation. So I remember you that an order relation on the set E is just a binary relation which is reflexive. X is less or equal to X. It is antisymmetric. If you have X less than Y and Y less than X, then X equal Y. And it is a transitive binary relation. If X is less than Y, Y is less than Z, then X is less than Z. So I just remember you this classical notion of an order, but it's partial order. It's not necessarily total order, partial order. And a poset is abbreviation for partially ordered set. It's a set with this order relation. So I need a few definitions, classical definition about poset. So there is a covering relation. Covering relation, if you have X less than Y, we say that Y covers X. The element Y covers the element X. If and only if you have X is strictly less than Y, and there is no Z between X and Y. If you have any element Z between X and Y, then Z equal X or Z equal Y. This is a covering relation, which means the interval XY, interval means all the elements between X and Y, is reduced to the two elements X and Y. And the poset can be defined by its covering relation, and it can be defined by a diagram which is called the assay diagram. So usually you put the element, the order relation is going up. You see this is the minimum element, and then you go, this is less than this one, this is less than this one. So this is the green edges going up are exactly the covering relation, and any poset, usually you just design the poset by a certain diagram like this. And you have a minimal and maximal element in any poset. Minimal means there is nobody below this element is minimal, there is nobody less than this one, and maximal means there is nobody bigger than this one. So there is two maximal elements in this poset and one minimal element. I will need this definition of a linear extension of a poset. A linear extension is our poset E is any map. If the poset has n element, if the character is n, is any map between any bijection between E and the segment 1n of integer, such as that if x is less than y, then f of x is less or equal to f of y. It means it's a labeling of the poset with the integer 1 to n, such that the labeling is compatible with the order relation of the poset. Example, see here is my poset with assay diagram, and here is the labeling 1, 2, 3, 4, 5, which is a linear extension of the poset. The labeling is compatible when you go up in these green edges, the number go increasing when you go up in the assay diagram.
But it's not unique.
No, it's not unique. Of course, it's a major problem in combinatorics to find what is the number of linear extension of the poset. And you know some very famous example. The example is take a Ferrer diagram, the partition of integer, and the cell, there is an order of the cell, which is a product of the order going from left to right and going from down to top, the product of the two natural order in the integer. So when you go right or left, then you have an increasing, you have a poset, and linear extension of this poset is exactly the Young tableau. Standard Young tableau is just all the possible linear extension of the poset defined by a Ferrer diagram, which is the product of the two total order on the integer. So your question, how many linear extension of a poset? A typical example is number of Young tableau, which is a famous formula, the Hooklands formula. So it's a major problem. There is very few examples of Posets having a certain formula which is called the Hook-Lens formula, meaning it's a product varied by a product. And I give you a second very famous example, the binary tree. I will not define the binary tree, but the binary tree is this picture. There is a root, there is a left subtree and a right subtree. And there is a total order on the binary tree. When you go down, you have a partial order. If you go down in the binary tree, then this defines you a certain order. And this is a possible linear extension of the binary tree. And the total number of linear extension of binary tree with n vertices is exactly n factorial. So the permutations are in bijection with linear extension of binary tree. Go back to the class of last year to define, to understand what is a binary tree, what is a permutation, what is a bijection between permutation and linear extension of binary tree. And for a binary tree, you have also a Hook-Lens formula, n factorial divided by a product of something. So it's a nice formula. So these are two examples, two famous examples, very classical, of linear extension of a certain poset. Next section, there is a strong relation between heaps of pieces and posets. If you look at these heaps of dimers, then there is an order relation. The order relation, intuitive relation is a dimers is above another one. This one is above this one. What it means? It means that when you log these dimers, you can say that this dimer was put after this one. Or this dimer was put after this one has been put after this one after this one, you see. But between this dimer and these dimers, I don't know. There is no relation. I don't know which one was put before. So there is a certain order relation, which is intuitively, these dimers, these pieces, I can, from the design, I can really say that this one put after this one, when they fall down one by one, but forgetting the order in which they fall down. It's equivalent to making the commutation. See, the commutation of the letters means, when you take the equivalence class, means you forget in which order the dimer fall down. But something remains. There is a certain order, which I'm going to define, order to be above a piece, above another piece. So the poset associated to a heap. So you take the heap here as a set, and I define the order relation as the following. The order relation related to the poset is defined as a transitive closure of this relation. This relation index C bolt is the following. Two elements of the poset, two elements of the heap are in relation with this relation, if and only if the projection alpha beta are in dependency, and the level of the first one is less than the level of the second one. See, if you have two pieces, the second is a level above, bigger than the first one, and the projections are in dependency. They are in competition. You are sure that the second piece was put after the first one. You see. Between this piece and this piece, you see. This one is a level, this is level 0, this is level 1. So the level of this one is bigger than the level of this one, and they are in competition. If I take the projection, they have a common cell. And this one is also in a competition with this one. So all these are in relation, this piece and this piece, this pair, they are in relation for this relation. But taking the transitive closure, you see, means that this one is going to be above this one. Because this is in relation, this is in relation, they are in relation. So taking the transitive closure means it's a sequence of pieces, starting from this piece, ending in this one, and each sequence between two elements, consecutive elements of the sequence, they are in relation like this. So I think everybody knows what is a transitive closure of a certain relation, which will give you an order relation.
Can you go back there? So it's like the first and the third piece.
This piece, yes, these two pieces, you see, are in relation for this, because one is at a level above and they are in competition. Now these two pieces are again in relation for this relation, but these two pieces,
Transitive closure.
these two pieces are not in relation. The projection is are disjoint, but they are in the transitive closure because this is in relation with this is in relation with this. Now this in relation with this.
But then for the cover, you want J is I plus 1.
If it's covering, yes, but in the case of covering, yes, it will be.
But you want those three pieces, the first and the third piece, also not to be ordered.
Mhm.
So.
But it's not necessarily the covering relation. You see, between this one and this one. No, it's a covering relation, yes.
It is a cover.
But the level is not necessarily I. This is level I, and see there is somebody here. So between this piece and this piece, it can be level can be more than can be I plus 2, I plus 3. No, it's.
So cover does not imply J.
Mm-hmm. So you have this, and then you come back here after a sequence of pieces covering, and then when you are here, between the two there is nothing, but they are covering, but not necessarily the level between I and I plus k. No, at all. No, it's not true.
The intermediate pieces are covered.
Mm-hmm. But this one, it says they are covering.
That is a cover.
They are covering, but the level.
They're on two different.
Yes, they come from two different, from the zero level, they come from two different sequences of pieces, which each one is covering the other one with level I plus 1. So this one are covering, but with the two level, the difference is bigger than 1.
So it will be easier if you make the Hasse diagram first and then get the poset.
Wait, this coming. Hasse diagram is coming, is coming. So here is the Hasse diagram. Here is a poset of segment. Here is a heaps of segment, and here is a Hasse diagram of this transitive closure. So you see now. So here in green you have the covering relation, and you see it's clear. This segment is covering this one, but see the difference of level is 2. It's because this segment comes from this sequence.
So what is the algorithm for drawing the Hasse diagram?
For the exercise, given excuse me, algorithm. Give an algorithm. Yes, if you are.
I mean, there's a general algorithm.
Yeah,
Maybe
yes.
There's a better algorithm.
Yeah. So it's a good exercise for computer scientists. People who like computer science get an algorithm to give the Hasse diagram of the heap. You take a word in the take any relation, take a word, so you have a heap associated with it, and give an algorithm to get the Hasse diagram in terms of word or in terms of heap. So here is so another example, say heaps of cycle. We will have a lot of heaps of cycle when we will work on path, and this is a poset related to the heaps of cycle, you see. In French, empilement. This is in French. Heaps is empilement de pièces. And I say the first time that in the Knut book, Knut doesn't like at all heaps, because heaps is a data structure in computer science. So we have a long discussion by mail to find another word than heaps, but I told him I cannot change the word. There is hundreds of papers in many domains working heaps of pieces. So after the long discussion, he said, okay, empilement is a nice word. I take empilement de pièces. The French word, this is in volume 4A, the last volume of his fascicule 6, about the satisfiability problem. So now if you take a heaps, you get a poset. In terms of poset, you have maximal piece and minimal piece. And this maximal and minimal piece in terms of poset correspond exactly to the minimal and maximal letters we have defined in terms of commutation monoid. There is two different definitions, you see. Maximal, minimal in terms of commutation monoid means that the letter can be put in the first position or in the last position using the commutation. In terms of heaps, maximal and minimal piece is maximal and minimal piece for the related poset. In fact, minimal piece in the heap are the pieces at level 0, and maximal piece are the piece you can take the piece and put it up without making competition with any other pieces. So this was minimal and maximal letters of class.
Can you go back to the
Here.
figure?
This one?
Yeah. So there the piece there, just below it.
This one?
Yes. Why is it covered by that piece on top?
Because there is a
There's nothing in.
there is nothing between.
That thing is in. Oh,
There is nothing
It's
between.
greater than
It's the elementary step.
You see the
The definition. You don't need transitive clause.
there is nothing between the two. This one, this segment is not even if it's going close to the green line. This segment takes the green point. So it takes the green point between this and this. It's covering. Here, this is so from this to this. You can go this way, or you can go this way. Okay, so now there is a relation between heaps and linear extension. Proposition. Take any word in the alphabet A, in the equivalence class, in the commutation monoid. So you have commutation alphabet and commutation relation. When you go to heap, the basic piece P is exactly the alphabet. The dependency relation, the complementaries, and take any heaps related to this. So take the associated heaps E equal in the isomorphism with the commutation monoid. So a word gives you this. Take the poset, and then the word of the class, the word of the equivalence class, are in bijection with the linear extension of the poset. So when you take a class, commutation class, you get a poset, and all the words of the class are in bijection with the linear extension of this poset. Example, take this word, sigma 1, sigma 2, sigma 4, in the commutation monoid, the generator of the symmetry group, or in the dimers. So take this word, give this heap, give this poset, and now this word is going to in bijection with this linear extension. The number, you put the label, you say, okay, this is the first pieces which fall down, sigma 1. Then sigma 2, the second pieces which fall down was this one. Sigma 4 was this one. Sigma 4, yes. This is number 3. The letter number 5, sigma 1, was this one. So you see, the bijection is obvious. When you put the linear extension, means you remember exactly in which order all the dimers fall down. So your word, it's a labeling, the word, the labeling of the poset related to the heap. If you forget the labeling, then you forget exactly the word. You just take the commutation relation. This means you take the heap. So the heap or the poset collect you all possible words of the equivalence class, and each word is in bijection with a linear extension. So I go back to my example of last time. There was this diagram, this heaps of pieces, alpha, beta, gamma, delta, and this is a possible linear extension. And last time, in fact, there was 5. Last time there was 5 possible words in some possible commutation relation. This is a poset associated, and all linear extension of this poset give you the 5 possible words that I get in last time with some commutation relation or this heaps alpha, beta, gamma, delta. This is alpha, this is beta, this is gamma, this is delta. Where alpha and beta are independent, gamma and this one and beta are independent, beta and delta are dependent, and gamma, delta are not independent. So go back to the diagram of last time, and you have the 5 possible words with the 5 possible extension, linear extension of the poset. So in summary, you have all this picture is a summary of everything I have done. So you have a certain relation, binary relation, which define you a graph, in fact, a dependency graph. The graph, usually, it's two vertex are connected by an edge if the two elements are in dependency. They do not commute. So this gives you a commutation monoid for the relation, the complementary of the dependency relation. Commutation monoid is isomorphic to a heap monoid. Heap gives you a poset. So the heap corresponds in bijection to the equivalence class of word, and each word of the equivalence class is bijection, the linear extension of the poset. So graph theory can be embedded in heap theory. Any graph can be viewed as a dependency graph of a heap. Now poset, now you can ask the question, is it any poset? Is any poset can be realized as a poset of a heap? And this is the next section. Oh no, not yet.
Partition lattices in higher dimension.
So complement, I go straight. Until what time I should, because I don't know how many. Are you free? Because usually it's 3:30, and so I will give you some complement. So every poset can be realized as a heap of pieces. Yes. So counting linear extension of a poset is equivalent to count equivalence class. It's the same difficulty. No, it's an easy lemma that any counting linear extension of poset, even of because if you take Young lattice, it's going to be a heap of diamonds completely full. There is no hole inside the heap. Yeah. So it's a trivial bijection, and it does not does not give any new insight. But it's good to know that counting linear extension is the same problem as counting words in equivalence class. So proof. Every poset can be realized as a heaps of pieces. So take a poset and take a set of chain. A chain is a sequence of elements. Each one is less than the other one. And sometimes classical notion is a set of chain is covering the whole poset, which means any element of a poset is belong to one of the chain. But I introduce a stronger definition. We say that the set of chain is strongly covering the poset. If and only if you take any pair of elements ST, S is less than T, and T cover S, so any pair of elements which are in the covering relation, then there exists a chain going through these two elements. Any pair of elements ST, which are in the covering relation. So you take any edges in the assay diagram, any green edges connecting two elements, then there is a chain of the family gamma going through these two elements. These two elements belong to a certain chain.
Is there an example where this does not happen?
Well, you take each chain reduced to a point. It's a set of chain covering the whole poset. Then I take a set of chain. Gamma is any set of chain, so you put enough. We should finish at 5 minutes, yes. This one is not working. So example, here is a poset. Here is some chain, the chain 1, 1, 1, the chain 2, 2, 2, and the chain 3, 3. There is three chains, 1, 1, 1, 2, 2, 2, and 3, 3. And if you take any pair of in the covering relation, then there is a chain. Here there is 2, 2. See, if I take this pair, there is 1, 1. So here there is three chains strongly covering the poset. Then I take this is notation. I take the set gamma and pieces. The basic pieces to be the subset of gamma. So I take any subset of this chain, and to an element S, I take PS to an element S of the partial order of the poset. I define the basic piece to be all the chain which goes through the element S. For example, here you see, I have my 3 chain strongly covering the poset, and here this element I have 2 chains going through it, 1 and 2, 1 and 2. Here you have the chain 2 and 3 and 3. And so this basic piece is a subset of the set of chains strongly covering the poset. This basic piece, so you can check that is exactly the piece I defined, 1, 2, 1, 1, 2, is exactly the subset of this element with 3 elements. 1, 2, 3 are the 3 chains. This is the example of the first lecture. You can convince by yourself that this will give you an isomorphism. The poset, the first poset is going to be the same as the poset associated to these heaps of pieces. And so counting linear extension of is exactly counting the commutation monoid. So number wing tableau, Klein formula, etc. Okay, I will stop with this proposition. And every Heaps monoid, I give you as an exercise, I will give you a solution next time. Any Heaps monoid is isomorphic to a heap of subset of a set X of monoid. Take any set, the heaps of subset, where the concurrency relation is a dependency relation is when 2 subsets intersect. Any heap can be viewed as a heaps of subset. I leave you an exercise, and we will finish. Okay, thank you.
If you're taking this course for credit, you should submit